Good morning, sir. My name is G. Harshavardhan, and my teammates are Saidattu, Avinash, and Prakash. The topic which we have chosen was Approximate Bayesian Computation and Simulation-Based Inference for Parameter Estimation in the SIR model. In this project, we explored ABC, ABC with tolerance, and neural posterior estimation. Now, we will start with the introduction to parameter estimation. Like in many complex systems, the likelihood functions are not tractable or easily computed. So it is a big challenge to us. So we need to estimate the model parameters based on observed data, but the likelihood function for the model is intractable. What is the solution to this problem? Approximate Bayesian computation, ABC, and simulation based inference methods. Now we will try to see what is the overall overview of the SIR model. The SIR full form is the susceptible infected recovered model is used to describe the spread of infectious diseases in a population. We have created this data set, and the key components of this data set are, yes, which is susceptible means the individuals who are not affected but can but are prone to get affected, and the second one is infected, individuals who are currently infected and can spread the disease, and the third category is recovered, individuals who are completely recovered and are no longer susceptible. This is the data set which we have created, and some of the parameters are, here beta is the infection rate, gamma is the recovery rate, and n is the total population, and these are the different kinds of equations which we have used in our model. Now, what is ABC? It is a method to estimate posterior distributions by comparing simulated and observed data. It is used when the likelihood function is not tractable. Okay, then what is SBI? It is a framework for parameter estimation using simulations and model comparisons. Includes methods like ABC and neural based approaches. What are the similar steps involved in both the methods? First, we sample parameters from a prior distribution. Then we simulate the data from the model using the above parameters. Then we compare the simulated data to the observed data, and based on the results we accept or reject the parameters. In this we explored three methods. The first one is ABC rejection. In this, direct rejection based it is direct rejection based on a predefined threshold. It is very simple but computationally extensive. And the second one is ABC with tolerance. In Unlike in rejection, we are not considering a threshold, but here we are giving a range, certain range. It improves efficiency, but it may also introduce slight bias because we are not giving any limits. And the third one is neural posterior estimation. It uses neural networks to directly estimate the posterior distribution, and it is very efficient compared to above both methods and scales better for large models. From here, my friend Saidattu will continue.
Um, Good morning, sir. Good morning, sir. My name is Saidattu, and I'm going to present the rest of the presentation. As discussed earlier, this is the first method which we testing. So ABC rejection algorithm, as mentioned earlier, and beta and gamma are the parameters, and we uh, sample them from uniform distributions, which we also assumed as a prior. So we simulate the data using this SIR model and compare the simulated data with the observed data using a distance metric. and accept the parameters if the distance is smaller than the threshold, and reject it when it is greater than threshold. So the challenge here are, as mentioned earlier, it's very expensive, and especially for the strengthened threshold, if the thresholds are not set it perfectly, the model may reject too many samples or may accept many samples. So it's heavily depends upon the threshold. So, and the second method is ABC with tolerance. So the major difference between the previous rejection method with threshold and tolerance method is, here instead of a strict threshold, we can accept the parameters up to a certain tolerance level. Means we are setting a limit to I mean max and min limit to the threshold. So benefits over this is it's computationally effective because we are not rejecting many, and so we can sample the required number of samples from the less computation itself. It's more flexible than the ABC rejection term, but the trade-off is, in the introduction to the threshold, uh, there will definitely a bias because it's not strict, and may allow for some error in the accepted parameter set. So the third method is neural posterior estimation. So similarly to the thing, this third thing is a little bit different from the both. So in here we simulate the data for a range of parameter sets and train the neural network on the simulation to learn the posterior distribution. Once the network is trained, we use it simple sample directly from the posterior. So benefits over this is much faster than ABC methods. Once the network is trained, suitable for large scale and expensive simulation. And for the project we have done, the neural posterior estimation has been reached a threshold. I mean, reached an convergence in nearly 150 epochs. And for all these data, we have to initialize the SIR values, and we consider this S naught, I naught, and R naught, and the parameters are beta, gamma, and we also estimated using from the uniform distribution as the initial values. So, and the time series output is the simulated data consists of number of infected and recovered individuals over time. It will effect on each other, and it is definitely a time series data. So comparison of models here is, ABC is simple, but it's definitely computationally effective. Accept the parameters only when the suited data is very close to the observed data. So ABC with tolerance is more flexible, as mentioned, and neural posterior estimation is fastest method of after training the neural network, but it takes time during the training, of course. It can handle a complex model and the large scale simulations. Now we can conclude some experimentation results from the previous models after the running. So regarding the efficiency, ABC rejection took the longest time due to the strict parameter, and ABC tolerance showed the faster results, and neural propagation estimation was uh, the most efficient, providing accurate posterior estimations as compared to the others. And the posterior distributions are visualized for alpha, beta, gamma, and in the next slides. And the conclusions are, ABC is useful for simpler models, and ABC tolerance is a good balance between efficiency and accuracy. And NP is most scalable and computationally effective method, and especially for the large models. In the future models, is exploring advanced neural network models, and apply the methods to the real world dataset. As in the current experimentation, we have generated the dataset and we have used that to the training. And these are the posterior distributions from the ABC rejection criteria, and these are the ABC from uh, from the tolerance, and these are neural ABC. As these posteriors are not accurate because the dataset is generated by us, but for a real-time dataset it might differs, and that's it, sir. Thank you very much.